There's no magnitude there, right? That's good. Yeah, good. Some method is better than no method. Yeah, good. I took off some points because there were 2 questions on that day. So yeah, it's not a serious thing. Usually I don't take off points in quiz, but yeah, in this case, I think there were 2 questions probably. I guess, yeah. Again, I'm not usually picky about this, but since it's in the beginning of the semester, just to not give you, just to motivate you into looking into. And typically, I don't follow it. If I get 1% this 3, 1% there's 2, I know that, oh, there were 3 questions. That's how I figure it out. Okay. There's, I posted a homework 2, which we will have it due next week. I think September. It's not September, no, August. August 30, of course. Too far. Well, okay. So midterm 1 is which apparently is it right. Sometimes I give a take-home component in the exam, in the sense that if there are 5 questions, I'll give 1 problem to take home, or you have to work on it and come bring it home. There are 2 pieces to that, or 2 possibilities. I can prepare the questions beforehand and post it about 3 days before the exam, and you bring the first question to the exam and you do the rest of them during the class. Or there could be 3 questions you do in class and then you take it home and then put on the 3 or 4 days back. So that's typically I decide it at the last moment. We'll see how it goes. So there was this question related to cross product. I think I just quickly looked at 3 of your answers. I think it is worth going through now. Just to so we had A, right here. A is, suppose you have some vector. It has to deal with magnetism. It really is a physical quantity. This is called the magnetic vector potential. But for now, we just have some vectors. And it's supposed to represent the magnetic field. This is the position coordinate. Okay, it's a general position coordinate. Let's say B is a constant, uniform. Is uniform. Okay. And our goal is to find del cross A. So that this actually is equal to B itself. So let's see how this goes. So this is 1/2 times del cross A. Del cross A is B cross R. Let's do this ith component. Ith component of this vector. So 1/2 times ith components will be epsilon I j k. J. This will be now k, so which is again epsilon k m n m n. Is that clear? That should be immediate. Bring this out. Let's 1/2 and move this around also. Preparing to bring in the identity there. So I moved this by 2, but that shouldn't change any sign. And we have gradient operator acting on B and on R. And so this is supposed to distribute, right? First it will act on this, and then it will act on that. I think cushions here. Distribute this, or go ahead and first actually distribute. So there is a distribution here, there is a distribution there. So let me do that both together. So this is delta I m delta j n minus of delta I n delta m. That's the two distribution from the Lewis-Evita product. And this also distribute, but now there is, let me first do the distribution. J M n and plus Bj or Bm. Okay. Outside the that's equal to now. Before we proceed further, notice I was specifically given that B is uniform, so this is 0. Derivative of a constant is equal to 0, so that does not contribute. And yeah, let's if this is not there, there are only 2. Usually there are 4. So there's only 2 of them. So that's 1/2 times m can be replaced with I and n can be replaced with j. Right. So this is the m. M can be replaced with I. N is with j. Minus of m can be replaced with j in this. So this is j, and n is I. Is that clear? what is this? The gradient J of Rj. How much is that? This parenthesis alone? Yeah, but how much is this?
It's 3.
That's correct. Yeah, but before that, actually, maybe that's not obvious. Let's do this. That's correct. That is 3 actually, but let's before I'll come back to that so that I can clarify. How much is this? Del J I. What's that equal to? Maybe that we haven't covered or that we didn't stress on that earlier. Like these are derivatives with position coordinate, and that's the position coordinate itself.
One.
Yeah, probably. 1 means there are 9 components right here. So it cannot be 1. So it's a tensor. Yeah, specified a little better. But 1 is a good, I think it seems like thinking correctly. So there are 9 components in this, which will look like E by first. So let me say this is D1 of R1, right? D2 of R1, D3 of R1, right? Is that clear what I'm writing?
Yeah.
1, R2, D1, R2. And how much is this now? Is that equal to? What is this? D1 R1. 1. That's derivative of with respect to x of x itself. That's 1. What's the derivative of y with respect to x?
0.
0. Derivative of z with respect to x, that's 0. See the pattern. That's 1, right? It is delta J. It's a tensor of second rank. Right? So this gives you 1 by 2 times di times del j minus of dj how much is that? 3. And this will be, you can replace j with I. So this gives you 1 by q, 3 times bi minus bi. So a lot of things happening. So the 3 minus 1, 2 divided by 2 is equals b. Correct. So that's a few things come together there so that it works out. So it's a good example in that sense. Question? Yes.
Why can't you make the statement that the BM is BI since you know del cross A?
Yes, you can. No, not I. The M cannot be I because I is a free index, right? Maybe ask me again. Which one are you saying?
So since the cross product of A, that's B, right?
This is B, yeah. I mean, I would like it to be B. Yes, that's what we want to prove.
So you can't do, so I guess like, because when I look at it, I see that the left-hand side is BI already.
Yes, that's because I asked you guys to, so this is in electrodynamics, typically you write P is equal to del cross A. Right? So what happens is that in electrodynamics, this is a solution or this is what you have. Magnetic field is the curl of A. That's what you have. And you ask the question, for what A will my magnetic field be a constant? that's the motivation. So for example, let's say electric field is equal to negative gradient of phi, right? That's the potential. So this is a familiar idea. Or the force is the gradient of energy, right? That's very similar. You can ask, oh, I want to create a constant electric field. What should my potential be? I think that's a standard question you ask. How will I generate a constant electric field? How will my energy or potential look like? And you would say, oh, well, what should this be? Suppose I would ask you, what should the electric potential be so that it's the electric field associated with it is a constant? So what will the electric potential be? Gradient of what is a constant?
Gradient of a car.
Gradient of a curve. That's going too far.
No.
Cannot have a curl to begin with because it's scalar, right?
I'm sorry, what was the question?
So the question is, if you want to generate a constant electric field, right, in your lab, what is the electric potential that will do that? Mathematically speaking, what should phi be so that when I take the derivative of that, it'll give me a constant vector?
To be changing.
Huh?
It has to be changing.
It has to be changing because if it is constant, it will give you zero.
Yeah.
So, and you also know that it has to be changing linearly because the derivative of a linear quantity gives you a constant. But you want a vector out of it, right? So that makes it a little, like after I write it down, it might be straightforward, but what is this phi equal to? So it turns out that if you were to have phi, like here, phi is equal to, let's say, minus E dotted with 1. That's not clear how it works out exactly. So that's equal to the electric field then is, or let's say negative gradient of phi. So this is what I was trying to motivate. I don't want to write electric field because then I'll get back the same thing. So I start with the right hand side just to check that this is actually true. So gradient of phi is equal to minus and the minus goes away. So it's plus of gradient. And I write it the opposite way just so that how? Right, that's what we have. Make some room here. Okay, clear. This is a vector. So this is, let's say, ith component of that. That's equal to the ith component will go here. That's clear because that's a free vector. This is a scalar product. So that's J E I. Also EKJ. And you have to take the gradient of both. And this is equal to, it will distribute again, J. Times J plus J del I. Be clear? What is this equal to? Gradient of the electric field?
Delta.
No, this is delta Ij. No, this is delta Jj, right? Oh, this is no.
It should be I.
This is I, right?
Yeah.
Okay. So this is equal to delta Ij times Ej. This one is not obvious, but then remember we're talking about uniform electric field. So we want to have a constant vector. So gradient of a constant is 0. Right? So that's 0. So that's 0, and which gives you I. Right? So that's the motivation I'm saying. So what we have, this is the relation we have. And then we ask the question, what should phi be so that I can generate an electric field. So I reverse the whole thing. I start from the right hand side. I ask the same question here that, okay, this is magnetic field is given in terms of this. What should be an a possible A that will generate a constant electric field? And it turns out that it should be this. It's a slightly more non-trivial. And does that answer your question? Probably not.
I mean, kind of, yeah. Like what I was saying is like, it definitely, I see where my statement's kind of wrong because like it's kind of like cheating because you know the answer in my
Yeah, that's what I was trying to
Yeah.
warn the other day also. Since you know the answer, it's very tempting somewhere in between to write,
Yeah.
oh yeah, that's, I see my magnetic field to put it.
Yeah.
But there are a lot of things that balances out here, like it's not straightforward.
Because you can let M equal I for the B, and then that'll give you the BI. But I
So-
see,
Tell that again?
so like so on the left-hand side, since that's BI,
Uh-huh.
you can make the BM on the right-hand side BI. So you let M equal I.
Again, so I is equal to M? No, M is equal to I.
M is equal to I,
But how do you do that?
because you know it's the same magnetic field. But that again
no,
is
no.
using the answer.
No,
So
no,
I
no,
see
no.
that.
Yeah, yeah.
That wouldn't be right.
Yeah.
But if
Like, because this is a dummy index, this is a free index, you cannot put them together. Right, so that will be, I would say wrong. Right? And that's what I mean, since again, if you didn't know the answer, you will not be able to.
You'll have, yeah, exactly. That's
And
what
you cannot do that. I mean, how about this? You cannot replace M with I.
You'll get the answer though, if you let M equal.
Yeah,
I.
but that doesn't.
Okay.
Right?
Okay, I see.
I think that's what I'm saying. No, you cannot. So that means you're making more than one mistake. You're getting the answer. You're doing this and then somewhere else you will again make a mistake. Does that help? No. So, or what you're saying is that if you start from an equation and you get an answer, that doesn't necessarily mean that all the steps are correct.
Mhm.
Right? So
Yeah.
that's one of the ways to look at it. Yeah. Else, in general, actually, this I mean, this is not. I'm not planning to do it, but this will be useful. Okay, so this is sort of a digression actually. That's not what I was planning to do, but let's do this anyway. Because this will be very useful for your electrodynamics. You come across a situation and or one of the most common derivative that comes in electrodynamics is that gradient of the magnitude of the vector. Right? That's one thing that can come. And the second is what is the gradient of a vector. Okay. So these are the two, and using these two, if you know the result of this, everything else you can build using this. So this is very useful to know this. To begin with, first one, is it a vector or a scalar? It's a vector acting on a scalar. This is the magnitude of a vector. So that will be a vector. So I'm going to write the result here and show that explicitly. So this is R hat. Dimensionally, it makes sense because this is 1 over distance. This is distance. So dimensionally, this has no dimension, a unit vector. Is this a scalar or a tensor? No, there is no dot product here. No dot product. In principle, often you can also imagine this as a, so this is often written in this form also. Okay. So, but you will, when you see any identity, there won't be a cross outer product here. You will actually see it in this form. So it's good to see it in this form itself. This is a tensor, two different vectors, no dot product, no cross product in it. And this, if you want, this is the identity vector. If you want, so see this as I and a j, right? So this is an I, that's a j, and this is delta IT. Another way of looking at this is, so this is the same as gradient of I, R of J is equal to delta IJ, which we explicitly just now did. Right? That's just that statement written in vector form. Okay. Now, how do we, so first let's do this. Okay. Or why is this important? Let's say, let me emphasize that first. Why is this important? You typically have a let's say you're doing electric field, no, electric potential, right? Electric potential due to a point charge is how much? Electric potential due to a point charge? No. Electric potential due to a point charge?
Charge of R squared.
1 over only R. Charge
Oh,
over R. The electric field is R
Sorry,
square.
yeah.
Right? Good. So it's Q over R, right?
Yeah.
So it is if you're in SI units, it is 1 over 4 pi epsilon Q over R. But this is math methods. I'm not going to worry about the units. I'm just giving you the techniques to do this. So let's forget the Q over 4 pi epsilon. Right? So we'll be dimensionally off. So this is not a potential now, right? So this is some function. And electric field associated with it minus del of phi should be should be equal to 1 over R squared. Right? It should come out like that. But let's show this. So how would you prove this? So let's begin with negative gradient of phi. That's equal to negative gradient of 1 over R. So this is a function. Don't think of this as an R, then it gets more confusing. This is actually a function and you're using chain rule. Right? So how do you take a chain rule? You would do first, you will do the R. Again, what I mean by that is that this gradient is dy dx, dy dy, dy dz. R is a function of x, y, and z. And that function happens to be x squared plus y squared plus z squared. That's how you want to look at this, right? So this is, you're taking the derivative with respect to of x of this function, which has this form. Right? So how do you take a function or a derivative whose functional form is there? You take chain rule, right? So first do it, the derivative of 1 over R. So that's plus 1 over R squared. By the way, what is wrong in this? It's a vector, right? So this should have an R hat in it. Vector, right translation, vector. So that's what we are looking for now. This is a chain rule, mine plus 1 over R squared. That should be straightforward, but then chain rule always leads to eventually hitting the argument, right? Argument is R itself here, so this is gradient of R. Right. Is that clear what I did? So what I'm saying is that for let's say if I'm doing d by dx of log of f of let's say g of x. No, what did I mean? Just f of x. So you would first do 1 over f and then do derivative of f with respect to x. In this case, we have derivative of x with respect to 1 over f of x is the same as minus 1 over f squared times derivative with respect to f. Right? The chain rule has to come in. So this is the chain rule. First do the 1 over R squared, and then you have to take the derivative of R, right? And that comes down to doing this problem. So for once, you should always do this. And next time when you do this, you don't have to evaluate it, if you remember this fact. So now, how do you check that that is indeed true or not? So once, do this. Right? So gradient of magnitude of r. So this, we can do this in rectangular coordinates. So this is I hat d by dx times x squared plus y squared of z squared plus j hat times, let me write it like this, so that because it's a derivative with y, which is identical, right? Whatever is a derivative with respect to x will be the same as derivative with y if I replace x with y. This is equal to I hat 1 by 2, put it in the denominator, x squared plus y squared plus z squared, and then 2x. And then the same thing with j hat. X over, this is r itself, so we have I hat times x over r plus j hat times y over r plus k hat times z over r, which is exactly vector r over r. That's r hat. Is that clear? Now, having done this, what we did this in rectangular coordinates. But this vector, this is the way this is written, this is independent of which coordinate system you are in. You could be in spherical coordinates, you could be in cylindrical coordinates. This has a meaning, gradient, irrespective of which coordinate you are in. R has a meaning irrespective of which coordinate you are in. R hat has a meaning. So this is in that sense, a geometrical identity rather than a vector identity. Right? So this is more powerful than doing the actual derivatives. Right? So that's your first relation. And the second relation we already did, right? This was delta ij. Now, where do you use this? So let's do an example where you actually do this again. So I would like to show where you use this also. So let's now consider a situation where electric field, oops, I changed it. So let's say electric field is now given, and let's say let me put in the quantities so that it's dimensionally clear. Right, so this is Q over. Let's put the Q here so that I have room for the R hat. This is basically a constant that will float around. You don't have to worry about that. This is the important piece. Now, what is divergence of the electric field equal to?
Rho by E0.
Rho by E. That's correct. Rho by E0. Very good. Very good. Because that's a Maxwell's equation, right? Maxwell's equation is this is equal to rho over epsilon naught. But what is rho in this case?
Charge density.
Charge density. What is the charge density here? Right. This is the rho over epsilon naught. Is that clear what rho is? By the way, rho is a charge density, a charge per unit volume. Right? It familiar? Should I? So this is the Maxwell's equation if you want. Right? So the question is, okay, that's a general law, but we are talking about a specific case. There's only one charge in the whole system. Correct? One charge whose electric potential is this, electric field is this. And then you ask, okay, what is the charge density due to a point charge? If you have just one point charge means it has dimension 0, right? So what is the charge density for a point charge? It's a tricky concept, huh? what is the charge density for a point charge? Shouldn't be zero. Shouldn't be zero.
That has to be non-zero.
Oh, it is, yeah, because there is a charge in there. But make it better. So for a point charge, so this is point charge. So say this just one charge. Let's say it is at the origin, No, let me not make that condition. So the charge density will be, charge density is a position dependent quantity. Scalar is like temperature, right? So the charge is, let us say, right on this camera. So that's where the charge is. I measure the charge density here. It's zero. There's no charge. I take a volume, charge per unit volume, right? That's how I define my charge density. I take my volume to be this. Charge is down there on the camera, right? No charge. There's a finite volume, right? So charge per unit volume is zero. I can take any volume I want anywhere and it will all be zero, right? Except if I were to have the volume enclosing this, but I said it's a point charge. There's really small charge, and the volume also can be really small. So it is zero everywhere, almost everywhere. Like if R is not equal to the position of the charge itself. So this is a variable R, and this is the position of the charge itself. Is that clear? But this is not equal to zero if R is equal to R cubed. In fact, so the question is, what is this equal to, right? There's only one point where the charge is. At one point it is something, everywhere else it is zero. Okay. So, but there is also one more issue with this. If I were to integrate over all space of the charge density, what do I get? So if I have given a charge density, and in this case, just one charge sitting at the origin itself, sitting on the camera, and I integrate everywhere over charge density. What do you get?
Infinity.
Okay. This is charge per unit volume, right? And you're integrating over volume. What do you get on the right side?
The charge.
Charge, correct? It's the total charge in the universe. If I integrate over the charge density, I should get the total charge in the universe. Is that clear?
Yeah.
Here, there is only one charge. So I should just get that charge, right? So this should just be Q. Assuming, yeah, that's Q small, right? Is that clear? But now maybe what is bothering you guys is that, oh, it's zero everywhere. And at that point, I don't know what it is. It is not very obvious to me, but you said infinity somewhere at another point. So you're doing an integral, you need to get a finite answer because it's a charge, Q, right? So think of a function which is zero everywhere, but you don't know what that other point is. At one point it is something, but it has to give you a Q, no other choice, because that's a necessary statement. So you ask, how is that possible? Because in an integration, if you take out a point, what happens? So for example, you do an integral of x squared, right? So this is x and this is x squared. You go from 0 to 1. Right? That's the area under that integral. But now I say that I'll take out one point on this, just one point, and that's half. So remove that point out, right? So that's basically, if you think of that as an area, that's the area of a line there. Right? If I remove that line, what is the area then remaining? It is still the same because the line does not have an area. right? Line has width 0. So the general statement is that in an integral, if you remove a point, answer doesn't change. Like you never worry about, oh, do I keep the boundary or not? Like sometimes we ask, oh, is there a difference in the answer if I go from 0 to 1 versus 0 to I approach 1? No, you can actually remove that line and still it's the same because the area of a line is 0. Right? So in that sense, if you say, oh, I remove one point, it should not matter. So the integral of 0 is 0, right? Everywhere it is 0, it should be 0, but that's not true. But then there is a caveat in this that this is all okay as far as it's not an infinity. If there is an infinity, then you have to be more careful. And the only way this can be true, this plus this can be true, is that this is infinity. Right? So let's say this is approach tends to infinity. So that is you have to think of a function which is 0 everywhere, but infinity at one point. And it's a need. It's not that you're trying to be creative there. There's no other way you can actually get this to. Is that clear, the issue that you're facing when you're actually physically working with a point charge, right? And point charges build everything, so it is a necessity. You don't have a choice. So since this is such a basic thing at such a basic level, you have a problem with not having a mathematical function. You define a function, and that's called the delta function, which you probably have seen somewhere on the. So rho for a point charge is equal to Q times the delta function, which basically means this. Whatever I wrote in there with all its issues, that's what delta function is. It's just that you find mathematical properties of that. This is a symbol that means that. And its integral has to be equal to Q. So what is such a function? That's a delta function. So if you want to imagine this, it will be like this, right? But not really going, it's just, in fact, ideally speaking, it's just at one point, right? So it should be drawn like this, right? Is that clear? And there are mathematical subtleties there, as I said. How does that integral go to a finite number when there is an infinity in there and it's only at one point? How does it work? Okay. So why I brought in all that is that's charge density, the divergence of the electric field should give me the charge density, and that for a point charge happens to be Q over epsilon naught times the delta function. That's clear? And the charge is at the origin, so this is not there. So that's position is 0. Clear? We need to now verify this. Now we have learned some techniques. Let's see if this can be reproduced, right? And there will be issues as we can expect because of all this. Okay, is the motivation clear? Okay. So we have electric field. Now we just do vector identities, right? This should we just operate this. So let's operate gradient of electric field, or just R hat over R square. And remember, we will use these two identities. These two you have to remember. Once we have checked this, we can use this again and again. So how do you do this? This is R hat, and this is the magnitude of R. But I don't know how to do a gradient of R hat. I have only learned how to do gradient of R, right? But I can convert R hat into R. So I say this is the same as gradient of vector R over R cube. And that is a gradient operator acting on this. Is this a scalar or is this a vector? This is a scalar, correct? There's a divergence of electric field, that's a scalar. So let me put in the index notation in here. So this is So I is a dummy variable now, and this is Ri times Rq. Which is the same as, now there are two functions here. I distribute, right? This is like f over g, the derivative distributes. So I can hit the numerator. So that's hitting the numerator. Del I Ri over R cubed. Correct. And notice I'm not specifying the coordinates. Try to realize that I'm not using rectangular coordinates or spherical coordinates or cylindrical coordinates. I'm going to use this. Right? And of course, I should be careful that I'm using the index notation, but that's just summation, right? We're just saying there are three components in there. So this is minus, because it's in the denominator. So that's 3 over r raised to 4. Right? So that's 3 over r raised to 4. Then I keep Ri alone. Maybe I should be careful. So first I leave Ri alone. So I leave the Ri alone. And now I'm doing gradient of I 1 over R cubed. So two steps is plus 1. Is that clear? What is this? The numerator? Del I Ri? Huh?
Del I.
Del I. And what is that?
3.
3. Good, right? So this is 3. All right, so very good. So that's 3 over R cubed plus Ri times del I now is again use the chain rule, right? So this is minus 3 over R raised to 4, and then del I vector R. That's not vector of scalar. And what is that equal to?
R hat.
R hat, right? But I want to write it as I, so this is equal to 3 over R cubed minus 3, that is 1 over R raised to 4, that is Ri, and this is Ri hat. What is Ri times Ri hat? What is this equal to? Try again.
R vector.
Or vector. Is this a scalar or a vector? On the left hand side. Be careful, because I think I'm using double notation. That hat was just to clarify that this is actually a unit vector, right? So this is the ith component of the unit vector, right? I times I, that's a scalar product, right? So no tensor, so it's a scalar. So that has to be a number then, right? What is that equal to? Dot product, right? So this is a vector dotted with a hat. Oh, did I say that correct? Yeah, it's correct. Yeah.
How do you go from left to right side?
How do I go from, okay, so maybe I should go back here, right? So this was Ri times gradient of R, correct? This is where we began from. This we said is R hat, the ith component of, this is R hat, ith component of the vector R. If you have two i's, that's a dot product. Agreed? So this becomes the dot product of vector R dotted with the vector associated with this, that's R hat. Did I help? I just repeated the same words.
Yeah.
Is it clear?
I have a question that if there is r hat, I can return the r hat as r vector divided by the.
That's the
magnetic
best. Then there is no confusion. Yes, that is, okay. So what you're suggesting is I should go back here and say that this is Ri times vector I over R. That's what you're suggesting. That's better. Okay. So that is equal to, now this is R dotted with R over R. Correct?
Yes.
So it's R square over R. That's much better. I like that better than R. Like R hat is a little confusing. Is that clear? Okay. Ken, questions? You're not comfortable.
It's okay. I'll look at it.
Okay, ask me again. But if we use that is R, that cancels out one of the R here. Right. So this is equal to 3 over R cubed minus 3 over R cubed. And that's equal to 0, right? Is that what we want? So you're saying that the divergence of the electric field is equal to 0, right? But is it 0? Is that a correct?
No.
No, right? Because we wanted the charge to come out, right?
Yeah.
But that's a delta function, right? It is 0 everywhere, except at one point. And notice we are at that one point, R equal to 0, this is 1 over infinity.
Yeah.
So what we have to say is that this is equal to 0 when R is not equal to 0. Okay. And this is a key piece of electrodynamics, that you have the gradient or the divergence of something equal to 0 everywhere, except at one point. But if you were to integrate this 0 everywhere, it's not 0. If you add up all these zeros, in fact, there is a point where it blows up, and that's the delta function, right? That's Gauss's law, if you want. Like that's the essence of Gauss's law, but that I will leave it to you guys. For you should ask the question, this delta function, how do you motivate that? Right. So that's for you guys. Okay, is that any questions here? So the basic idea I'm trying to say is that in electrodynamics and in various other fields, you will have to do operations like this. And this operation requires 2 identities. If you know how to do that, you can do this in 3 steps. And I made this into 5 steps, but this is only 3 steps. So you don't have to go into rectangular coordinates and do each derivative. If you know these 2 identities, you can get them. Like life becomes much easier. So concentrate on what this is, understand that, and then every time you come across it, you can just start doing it. And trust your result. If it is 0, it is 0. Like it is 0 in the sense it is everywhere 0. Otherwise, you say, oh, I'm not supposed to get a 0, but what's happening? And that is a catch there in the sense for you motivate that delta function, which I let you guys. Okay. Okay. So, you have 20 minutes left. Any other questions? Yes.
So when you operate on R as a function, like in what instance do you know that R is a function and not? Like, does that have to be like told to you before?
Always it's a function, right? So your question is that, I think what you're asking is, I think I gather it. So you're asking gradient of R, right? How do I know that this is actually a function?
Right.
It's a dependence. But notice, do this explicitly. Okay? This is a derivative with x, right? D by dx of R, right? Plus j hat d by dy of R plus k hat d by dr of dz. Right? That's what explicitly it is. And now ask the question, what is this? Like that, how does the magnitude of a vector change as you go in the x direction? That's the question you're asking, right? So you have the length of this vector r, right? Only the length, not the direction. How does the length change as you go from this point to this point? If I change my x a tiny bit, how does my length change, right? That's this quantity, right? And r is a function in the sense it is x squared plus y squared plus z squared. In that sense, it's a function, right? So, yeah, when do we know this? Almost always. That's one way of trivially saying it. But then whenever you don't know, like ask what is r and what is gradient? Oh, gradient is always x, y, z. But then I don't encourage this too much, because then you will enter into doing long calculation with x, y, z. The moment you go into rectangular coordinates, there will be 27 components and you have to do all that. It can get very quickly tedious. But in the beginning, everything is tedious. You once, twice do it, and then you see a pattern. And once you get the pattern, then you say that, okay, I don't have to do this again and again. I just have to repeat it. So this is the pattern. That's the tedious part. Right. Does that help? So, and you'll see it. I mean, at least in electrodynamics, this comes again and again. But once you get this, then at least that vector part takes a backseat, and then you can start concentrating on the physics of it. So hopefully it helps, but it takes some time. Any other questions? Yes.
If you wouldn't mind.
Yeah.
Excuse me. So the del vector and r vector right there being a tensor product, right?
This is a tensor product here.
So you can just take that equation and make it a tensor product over r cubed.
R cubed.
Like instead of doing it 5 steps, you were saying you could do it in 3.
Oh, no, I think I meant 5 steps in the sense, since I was explaining this, it is 5 steps, right?
Oh,
So in principle, I can write down my answer immediately. Oh, this is 3 over r squared. This is like, with some practice, you don't have to write these 3 steps explicitly. In that sense, it is 3 steps. But even if it is 5 steps, it's okay. Like if you want to count this as 5 steps, that's okay, 5 steps. Yeah. So, but I'm saying conceptually, this is very simple from here to here, or even mechanically speaking, it's very less number of rules going on. But this is tedious, right? If I were to do the same thing using this rectangular coordinates, that can be very tedious. Like, and it will be again repetitive, and you will yourself come with that thing. Oh, I see the pattern. I'm doing the same thing again and again. But I'm just showing you the pattern so that you can do this. Okay. Yeah. So since we have 15 minutes left, I'm supposed to do something else, but that's okay. I want to convey one more thing. So I left this open, right? I didn't want to go into that discussion because that's the whole electrodynamics in there. This is 0, but that's supposed to be delta function, correct? How do you motivate that? So that's essence of the Gauss's law. So let's do this. So let's actually, so now what we have shown is that we would like for a point chart, right? So let's just summarize the important points. This is Q over 4 pi epsilon naught, r hat over r squared, right? That should be, that's an electric field due to a point charge. Divergence of the electric field has to be equal to the charge density, right? 1 over epsilon naught times the charge density for a point charge, which we say is Q over 4 pi, no, Q over epsilon naught times the delta function, which is at the origin, so it is r. Okay, that's good. But we also showed that if I start from the first line, substitute on the left-hand side of the second equation, I get 0 everywhere, except I don't know how to do r equal to 0 because that's going in the denominator. So those are the three results that we can compile at this point. And there is an issue in these two. This is not consistent three equations in the sense that if I were to integrate the third equation over all space, okay, this in principle should be 0, right? Because I'm adding a lot of zeros. Right? I'm only missing 1 point, and I argued that if I miss 1 point, that's okay, unless it's infinity. But at this, since we haven't introduced properly the infinities, so it's not very obvious what's happening. So this is what you say that, okay, let's investigate this. So I want to avoid that 0. Right? How can I avoid that? So this is a volume integral. If I do this volume integral, I will encounter the r equal to 0. And then I say that I can drop that r equal to 0 and it is 0. But we also have divergence theorem. This is the importance of the divergence theorem. This is also equal to a surface integral, the r, so the a, right? The a dotted with e. Is that clear? Is that familiar? Right? That's the divergence theorem. And now we are in a different, now we are not doing volume integral. So we are not encountering that infinity. Right? So now we are saying that is a point charge at the origin. This is a surface. In principle, I can take this all space also to be on a sphere, right? We do it on a sphere actually, on a sphere of radius r, right? On a sphere. And still that should, all that argument should go through. So I have a point charge somewhere, which at that point I expect some infinities, but now I do the whole integration here. But using divergence theorem, I go to the surface alone. And on the surface, this is very well defined, electric field. So now I'm not playing with infinities. Now I know that I trust my answer very well on the right hand side. Right? This one I don't know because at one point, oh, what's happening there? Maybe that's an infinity. How do I deal with infinities? Right side is on a surface, and now you do this on the surface, calculate this. So this is dA. dA is dA is dA itself. Let's say, what's dA? dA is this vector here. So dA is r squared d sigma. Right? This is a solid angle and the unit vector r hat. That's a solid angle, familiar? D theta, d phi. So dA would be written as sine theta, theta, d phi, r hat. Is that okay? This is the area, small, tiny area element on the surface of a sphere, right? This is the radius of the sphere, and that's the direction of the area is a vector, so that's r hat. If I were to integrate this, first let me say, what do I get? dA. It is not a vector. Okay? What do I get dA? If I integrate over this without the r hat, so this is the area element, right, on the surface of a sphere, a tiny surface. So this is the surface, and suppose that's your tiny element, right? That's your dA with a direction associated with it. Drop the direction. So it's the magnitude of that tiny piece of area. What do I get if I add up all the areas on the surface of a sphere?
Pi r squared.
4 pi r.
4 pi r, sorry.
4
Yeah.
pi r squared, right? So that's 4 pi r squared. Good. Right? Now tell me, if I were to integrate the vector area, what do I get?
Volume.
No, so still the area, right? Dimensional is still the area. The only difference is that it has a direction. Think of it again, you have a sphere. There is a tiny element here that has a direction. Think of it physically. Now I'm adding up all those vectors on the surface of a sphere, right? What do you get? Geometrical. It is not a, it is nothing, it's a very simple answer. It's a vector, notice. So for every vector on the North Pole, there is a vector on the South Pole. It's in the opposite direction. On this, it is on this side, right? So they all cancel out in zero. Vector area goes to zero. And this is the magnitude of the area. If you were to take the vector and actually add up all, they go to zero. Cannot help it, right? That's okay, but that's just a side thing, just to get you familiar with dA. Here we are doing dA dotted with E, right? So let me write that. So this side say is d sigma, right? A short form for that, right? So this is R square. Again, this is very conceptual. So notice what's happening. The R square d sigma is R hat. Let me write, so electric field we know, let me write it in this form. There's R hat, that is Q over 4 pi epsilon naught, but before that there is a R square, and that is Q over 4 pi epsilon naught. I just wrote it in some order. With me? R hat dotted with R hat is 1. Okay. That's the simplest part, not much richness in there. R square cancels, that's very important. R square cancels, and this R square is coming from geometry, right? This is the geometry of a sphere. If our sphere was in the nth dimension, this will be different. In a cylinder, it is R. Right? This square is coming from the geometry, number of dimensions of our space. This R square is the electric field R square, and they have to cancel, correct? Because we want to charge, which means to suggest that the electric field R square, it is not a coincidence that it is 2. It is because our dimensions of the space is 3. That's an indication that our space is 3-dimensional. If our space was 10 dimensions, it will show up here, right? And there are tests done to check that actually is that 2 or something else, right? So this is a signature of dimensions of space. In that sense, it's a deeper concept. But for us, that cancels, right? So it's good, that cancels out. Now everything is constant right here. There is no theta and phi in here. I can do this integral, which is 4 pi. Right? So 4 pi cancels out this. So that's equal to Q over epsilon naught. Notice I did not have the idea of infinity here. This is concrete. That is, on the left-hand side, you will say, oh, I don't trust this. It is 0 everywhere. And then you're saying there's an infinity at one dot, at one point. I don't trust this mathematics. This is all stupid. But right side, you cannot deny. There is no denial of the right side. If the right side is true, the left side has to be true. So you have shown that if the left side is a delta function, this is dqr, right? Delta function. So you've got a property of a delta function in a very, if you want to obey Maxwell's equation, this has to be true. So delta function property is a necessity. So in a physical sense, you prove. Right? This is Q over epsilon. Here. So you cancel that, that's equal to 1. Is that clear what has happened? So you conclude, right, that del dot E is delta function B. Right? I showed the delta function because I didn't want to get into the delta function part. But if you had just said charge density here, you would have said that charge density is a delta function. So this is very, or that's a first principle in electrodynamics. There is one more thing that happens that was done by Maxwell. You do the same thing for magnetic field. Right? Where is the source of the magnet? So this is a source, right? Where is the electric field created? It's in the charge, right? When we say sun, right? Sun, there are rays coming out. How much energy? How much ever far you go, if you take a full sphere around it, you will always capture the energy coming out of it, which means to say that the flux of energy coming out of the sun is a property associated with the sun itself. Like the electric field, the flux of the electric field, which is the divergence of E, is a property associated with the charge itself. It tells you where is the source, and in this case, the source is right at the very point, one point at the center. Nowhere else there is a source. Nowhere else you add up an electric field. Everything is coming in from that. So that's a concept. And yeah, I can stop there. So this should help you with the electrodynamics, but this was not what I was planning to do. But this is, we can think of it as an extension of the vector calculus we were dealing with. Typically, it's also good to do divergence theorem and Stokes theorem. So we will see that somewhere else. Okay. So next class we will do curvilinear coordinates. So all this in a very general framework. What is the so how does the gradient and curl work in a general coordinate system? So I posted a homework which is due on next Friday. I think it can still be done because I'll finish it on Friday, but the next homework probably it might get postponed somewhere because we lost. Like this was not what I wanted to do today. So somewhere it will get adjusted.
So the next homework due is Friday?
Friday, yes. I haven't taught it yet, so I will start it on Monday, but I think I'll be able to finish at least the homework component of that. I'll be able to finish on Monday itself, I think.
Plus there are videos.
And there are videos. Yeah, that's a good thing to do. Yeah. Check out, you know what he's meaning? The videos?
Yeah. The past videos.
The past videos. So if you look into the third lecture, if you go and do it, so then you can do the homework. But I plan to do that on Monday, so you can wait. So I'm not asking you to go and check the video because that's another 1 hour for you. So if you're curious, you can. Yeah. Okay.